Hello, I'm Cadet Marchillo, a senior at the United States Military Academy at West Point. I'm a geospatial information science major in the Geography and Environmental Engineering department. Today I'll be discussing the generation of 3D models to augment geophysical concept learning. Despite its status as the world's premier ground combat force, the U.S. Army continues to rely on two-dimensional maps for mission planning and to educate its leaders in current tactics, as well as presenting those tactics as executed in historic battles. The use of enhanced visualization techniques that include augmented reality and virtual reality can greatly improve these abilities. Furthermore, the use of these techniques transcends the U.S. military and is applicable for all geophysical professionals. The methods identified in this research can strengthen student understanding of our physical environment without leaving the classroom. The inspiration of this research came from the West Point History Department's desire to have some form of either AR, augmented reality, or VR, virtual reality, exploration of the famous Battle of Pointe-du-Hoc, France during the D-Day invasion. The creation of an iOS application utilizing the three-dimensional mesh was the catalyst to find other avenues to present this 3D model. The objective of this research was to identify a method to create a 3D terrain for enhanced visualization purposes utilizing aerial photographs captured with consumer-grade drones. The objective was achieved using over 10,000 images of Pointe-du-Hoc, France, to recreate the notable terrain of the famous World War II battle during the D-Day invasion. We achieved this by using a photogrammetry software called Pix4D. For our methods, we used consumer-grade drones equipped with high-resolution RGB cameras that captured over 10,000 images of Pointe-du-Hoc, France. These images collected by the drones were scrubbed to remove images that were blurry, affected by weather, for example, raindrops in the lens, or otherwise unusable. These drones conducted a gridded and free flight path in order to collect these images. Of the 2,951 images used for processing, 2,764 images were calibrated properly using Pix4D in order to georeference the model. As you can see in the image, the green and blue images were calibrated properly, while the red were not calibrated. We had issues mostly on the western side of the cliff. 6 different model settings were tested to assess the effect of resolution and texture manipulation on the resulting mesh. These consumer-grade drones have internal electronics that know exactly where it is at all times. Pix4D uses this feature in order to use aero triangulation. What this does is it takes multiple photographs and finds the same point in each photograph in order to create an XYZ coordinate and create the three-dimensional point, which is a tie point. These tie points result in a dense point cloud that had less than 10 centimeters of spacing in between them. The 2D key point matches show the major points of emphasis. From there, the initial point cloud is returned. The initial point cloud return was cluttered and undesirable. This is a large part to do because it is difficult to find tie points in an ever-moving ocean. You can see the results in the initial mesh as well. It looks as though there is somewhat of waves or even a cloud-like buildup in the shores. From here, we have to go back and edit the initial point cloud. The picture shown is the editing process of one of the cliffs. Editing process takes out the undesired points within the dense point cloud. It took us about 9 iterations to go back and clean up that point cloud. After the 9 iterations of going from point cloud to generating mesh and going back to point cloud to clean it up once again, we generated our final point cloud. The image right here is the final point cloud of the northern point. You can still see it has the pixelated attributes of a point cloud, but it's dense enough to have a true shape. From there, we generated the final mesh. Here's a high oblique angle. From here, we process a flyover within Pix4D. You can see as we move from east to west, you can see the daunting cliffs that the U.S. Rangers had to scale in order to assault through the objective. The 3D model that we created is viewable in a multitude of formats that include an iOS application, 3D printing, GeoView 3D, and an augmented reality sand table created by the Army Research Lab that we call ARES. The augmented reality sand table utilizes a projector and an infrared Xbox Kinect sensor to continuously calculate the sand heights in order to model terrain in a pseudo 3D environment. This tool provides a tangible medium that can be manipulated to demonstrate geophysical concepts and processes. In addition to the initial projector and infrared Xbox, we've hooked up an HTC Vive to register the 3D model of Pointy Hawk with the sculpted terrain on the sand table. The HTC Wand controller is used to explore the 3D model through interaction with the 2D historic map used by the Allies to plan the invasion. As you can see, Delta Company moved up on the western side of the cliffs and assaulted through. In addition to Echo and Foxtrot on the eastern sides, they assaulted many gun positions and outposts. GeoView 3D, also known as the Geospatial Virtually Immersive Evaluation Workstation. The point cloud from Pix4D was exported as a LAS file to display on GeoView 3D. The GeoView 3D is a 3D television accompanied by infrared tracking cameras that facilitates assessment of data quality and quantitative analysis of the data by allowing for complete movement throughout the dataset. GeoView 3D was created by Dr. Matt O'Banion, USMA-GIS, based off of a platform created by Dr. Oliver Kralos, UC Davis. A team of West Point cadets created an AR iOS application for iPhones with an A9 processor or better. The team utilized an OBJ file of the 3D mesh exported from Pix4D. The app geo-references the 3D terrain with a 2D historic military map. This tool is practical for visual learners and provides an interactive experience. More research needs to be conducted to fully understand the errors in the mesh process to fully harness the power of 3D models for geophysical assessment. Specifically, the quality of geolocation accuracy and measurements of features represented by the model. Initial testimonies by cadets and professors at West Point supported the suggested benefits of the project both academically and militarily.